Yeah, I've just brought a bunch of these GU10 retrofit LED light fittings. So I thought it'd be a good time to tear one down, take a look at it, maybe draw out the circuit diagram and see how it works. So let's get straight to it. Yeah, I brought 50 of these from a well-known auction site for a very good price. So I thought I'd take a look before I start installing them, see if they're safe and whatnot. Let's have a look. Yeah, so it looks like we got 5 LEDs in series. Looking at it, right, let's find a screwdriver. So we need a little Phillips in here and see what we got in here. I would suspect it would be a capacitive power supply in here. It's usually quite common in these. You can get the switch mode ones, but looking at the 5 LEDs in series, I would have thought it would have been. Let's have a look. Try and get this done in one take, because I ain't got a lot of time. Oh yeah, that's a nice bit of heat shrinking done over there. Some knife so we can rip this down and take a look. Yeah, so I always recommend ripping these things to bits, just have a good look to see if it's all safe. And so I did get them for a good price. So I worked out about £1 each, which is very good. Let's have a look. Be careful, I think this. There you go. Huh. Let's have a look. I'll see if I can zoom in a bit more for you. There you go. Wrong way. So yeah, it looks it's fused on the main side. That's like 1 amp, little 1 amp fuse in there. Yeah, it's your typical capacitive transformerless power supply. Yeah, we've got a bridge rectifier. Yeah, we've got some SMD transistors down there. We've got the X-type capacitors, moving cap, MOV. That MOV looks like, yeah, that MOV's on the load side. Usually you get them on the main side. Quick to show you that. Right, so we can trace this out and see how it works. Maybe do a few calculations just so you can get a appreciation of what everything does in there. And it looks pretty safe. This isn't non-conductive anyway, because you've got to remember with capacitive power supplies, they're not isolated anyway, so effectively you've got mains this side. I know the voltage has dropped and whatnot for all these, but I think what we do now, I think we cut this out of its housing just so I can I'm trying to look for my tin snips now, wherever they are. Not all. What have I done with them? Ah, there they are. Right, let's just rip these out and we'll take a closer look. Get it going. Take some readings. white now, I forgot to say, warm white, so the voltage drop across these LEDs, white LEDs, usually about 3.1 volts, so you're probably looking at 15 volt output. I don't know how they've designed the current rate. I would have thought I'd probably designed them at 30 milliamps a throw. I would have thought. We'll have a look at that in a minute. So let's trace this out anyway on a piece of paper and take some readings, and we'll take a look. So let's just get my camera right. I think that'll do. I'll just draw this out quick. I'll zoom in a minute once I've done it. So you got live fused to there. So we got our live. We got a little fuse here. I don't know if you can see that. Probably need to. Well, I'll draw it out first, and then we'll take a closer look and get this done quick. Yeah, we got two of these X-type capacitors in. They're actually in parallel, but you've got to remember with capacitors, they work on the opposite basis to resistors. So these in parallel would be effectively doubling the size, as opposed to resistors when they're in parallel. It actually brings them down by half. So we've got two of these in parallel, and they are 125J, 400 volt. So that'd be, I think they're 1.2 UF a throw, so that'd be 2.4 UF. And yeah, there's bleeder resistors there. They're SMDs, 514. So two of them in series, 1 meg. So I should bleed resistor across there. We'll talk about that in a minute. What the purpose of that is. 1M, 2.4 UF. Then we got, yeah, it's just typical bridge rectifier. Well, not that neat, but you'll see in a minute once this is done. For those of you who don't know what the bridge rectifier does, basically all that's doing, because we've got an AC current going in, it's just going to smooth it out so we can get a DC out. You probably know that anyway, but I thought I'd mention it. So that'll be our DC positive, negative, and neutral. Looking at the neutral, that just looks like, yeah, it's just going straight through there. So usually these, usually you have the MOV protection here, but for some reason I put it this side of the circuit. We'll have a look in a minute. And then we can just see that, yeah. SMD 104 across the load, that's 100k. 100k there. And then we got the MOV this side. Let me just have a look and see what size that is. That's 20 volt MOV. We'll talk about that in a minute. So yeah, we've got that again going across the load. Yep. Across there. I'm trying to remember my MOV symbol now, but I think it's right. 20 volt MOV. And then we got electrolytic 100 UF 35 volts. That would make sense, because rule of thumb usually they say whatever your voltage out is on the load side, have a smoothing cap double the voltage, especially in capacitive power supplies. So yeah, so that's typical, I think. Yeah, plus minus. Well, it's looking a bit crap at the minute. Not to worry. What we got? That's going. Oh yes, current limiting resistor there for the LEDs. That's SMD 100, so that would be 10 ohms. So that's series with the LED. 10 ohm current limiting resistor, and then all we got then is the LEDs. They're in series, but we'll verify that in a minute, but you can see they're in series. There's 5 of them in series, so I'll quick draw them in quick. 1, 2, 3, 4, 5. Well, I think that's about it, yeah. So that's just a quick sketch of schematic for that, and you can see that. It's a bit poor, but we're take some readings now. I'll run through a few simple calculations, just so you can have an appreciation of why the original designers put 2.4 UF in there, why the 100k resistors in there, why the 10 ohm resistors in there, and by the end of the video we should have a good understanding why. And well, that's it. Let's have a look. So I'll just strip these wires off and somebody bang 240 volts in it this side. I don't recommend doing this because you have got 240 volts along here and it can be very dangerous if you don't know what you're doing. You don't really, I know they've marked these live and neutral here, but you don't really need to worry about the polarity, obviously, because of the GU10 fit in there, you know, they're not, you can go in anyway. So I think that's just for the PCB designer. Let's have a look then. Right, I'll just bang this in here. We take some readings. Right, so we'll bring this forward. I don't really want to promote this circuit to you because it's not the safest, so you just got to know what you're doing. I'll see if I can get everything in one. I think we've got most of it in there, haven't we? Let's have a look. Right, it's probably going to freak the camera out me turning it on, but what I want to do now is just take some readings of the LED voltage, so I'm correct on the, I'm sure it'll be 3.1 voltage drop across the lot of them. So you're probably looking at a total circuit output voltage of around 15 volts, but we'll verify that. And let's see if we can go, I don't know if I can get my meter in here. Yeah, I think we can. Let's just switch it on. Might freak the camera out a bit. I've got auto focus on at the moment, so let's see how we get on. Let's have a look. Yeah, it's terrible really, but anyway, let's just do these quick voltages. I'll do a current reading as well across them, and then we'll do some calcs and we'll take a look. So voltage across these is, I can't really see what I'm doing. .1 volts, yeah, as I suspected. The total output voltage is can't see because I'm blinded. Well, it'll be 5 times 3.1, so 15 point odd, yeah, so I was right on that. I'll just do a quick current reading. Remember to change your leads over. Thank you, Fluke, for telling me that. I suspect, well, I don't know, let's have a look. Let's just short these out. One of them anyway, if I can. Can't see. Let's do one of these. Can you see that? No. Yeah, it's around 30. Yeah, so we'll write these down. Just switch this light off now. It's getting me down. Right. So these, oh yeah, I forgot to say, these are rated at 3 watts. These GU10s. So 2.4 UF. So let's just do a quick calculation. I know they're all in series. 3.1 times 5. That is 15.5. Yeah. So basically, all that is you could represent it as a big 15 volt Zener diode if you like, but we got a 3.1 voltage drop across each one, which is total output voltage of 15.5. Oh, I forgot to put the value down for that. It's 100 UF. 100 UF. Yeah, I think we've got everything we need to do do a few calculations. Right. Just move that out of the way. Right. Well, there'll be a few equations that we're looking at. Effectively, the capacitive power supply, basically it's a current source. It's like a constant current, and that's determined by the size of the main capacitor there and this current limiting resistor here. I think what the designers looked at, he's looked at the output voltage versus the current drawn. I think it's looking at it's going to be based on about 30 milliamps. 30 milliamps a LED, which is pushing it really, but I expect they're getting the most light they can out of it. So that's these capacitors 2.4 UF, that was chosen to deliver specific current. Right, looking at that, we're probably going to need about 160 milliamps. I would have thought, looking at 30 milliamps a throw and 15 volts and whatnot. So what we need to do first is to find the reactance of that capacitor, and reactance basically is equivalent to resistance, so we'd use reactance then with our basic Ohm's law to find out how much current that the capacitor can deliver. So let's have a look. So reactance is X is what we use for reactance, and for that what we do is 10 to the power of 6 is 2 times pi times F times C. F is the frequency, and C is the capacitance in farads and microfarads and whatnot. So based on what we got there, we could X, you can see that X, so our reactance of that capacitor there would be 10 to the power of 6, 2 times pi times 50 Hertz times 2.4 UF microfarad. And then just key that in quick. And so 10 to the power of 6, 2 times pi times 50 times 2.4 UF. And we're looking at the reactance or equivalent resistance is 1326. Round it off to that. So that's the third, basically then that's 1326 ohms. So now, once we've done that, we can use our basic Ohm's law now and figure out how much current that's able to deliver before it starts getting stupid or voltage starts dropping sillily, you know, and things like that. So let's have a look. Ohm's law. We all know Ohm's law as V I R. Yeah, the Ohm's law triangle. What we want, we need to find out what the current is going to be. So I equals V over R. So we've got to have our voltage, which mains voltage 230 in the UK, to 30 over 1326 equals that. 230 over 1326 equals, you know, probably looking at about 173 milliamp. 173 milliamp. Yeah, so there's going to be a few losses. We've got the diodes. We're going to have some losses there, and the losses in there depending on the quality of the capacitor. So I think what the designer was doing, he probably looked at his output first. You know, he's got 5 LEDs, 15 volts. Yeah, and he's looking at 30 milliamps for each LED. Let's just say that. You know, so he's looking at 150. You know, with that and with that current source capacitor there, is able to deliver 173 milliamps quite comfortably. So always remember, put capacitors in parallel, it doubles them. So if we was to double that again, put another 2.4 UF in there, which should give us 4.8 UF. You know, that would give, you know, we could get 346 milliamps out of it. You could probably go on forever until you got, you know, an amp or something, but then it starts getting a bit stupid then with the size of the capacitor and the cost of it, you know, and things like that. And that's when it's time to start looking at switch mode power supplies or linear ones and things like that. Right, let's have a quick look and have a run through and have a quick look, show you. Right, with capacitive power supplies, they need load on them all the time. If they haven't got load on them, things start warming up, and that's why we got this 100k actually, let's work from the left. Actually, this 1 mega ohm resistor that's in parallel with the capacitor. They call that a bleeder resistor. Obviously, we've got 2 large capacitors in there, and once they're at mains, well, it's going to be once they're at mains voltage. Pull your light out, they're going to sit there, so they need discharging somehow. Rather than being discharged through you, they'll safely be discharged through the 1 mega ohm resistor. That's typical size for capacitive power supply. Obviously the fuse, we all know what that's for, protection. Bridge rectifier takes an AC current, takes it into a DC current. We'll talk about that in a moment. The 100k there, that's current limiting. That's there. That's basically in parallel with that. We did say we've allowed 30 milliamps per LED, because that's an orders of magnitude more than the 10 ohm, obviously. So we're going to have a small amount of current running through here, so it'll probably be around 3 milliamp. And that, Kirchhoff's current law, you got that there, you got one going there. So if we was to lose, so we was to have a break in here, that'd be open circuit, and we'd still have 3 milliamp in there, so it wouldn't go stupid. Because in capacitive power supplies, if you've got open circuits, you get that full amount of current running through no current limiting resistors, and things start getting warm. I may show you something later. Why we need that. The MOV in there's protection, suppression, voltage suppression. Again, that is this side basically is for protection. That suppresses anything over 20 volts. So if you get any peaks or surges, it just take it down to ground that way rather than going through your circuit. And this electrolytic here, that's used for smoothing again. I know we've got a full bridge rectifier, but effectively we'll be having like bumps like that. And once it goes through the actually the waveform will start off like sinusoidal, then it lifts it up, then you have a few bumps and peaks up there, and that electrolytic there will smooth it out to a nice DC current there. Again, this little 10 ohm resistor in here, that's current limiting again. For the designer's thrown that in for current limit because these two here work in tandem with each other. Change that one, you can get a different current draw. Obviously change that one, you get a different current draw. But after we've got 240 volts coming in here, and once it goes through the bridge rectifier, it effectively, because you got RMS 240 is, and then you got peak to peak. I'm not going to go into it, but basically what happens is you have 240 volts going to the bridge rectifier, times that by 1.4, and on the output you're going to have 336 volts DC on the output of the bridge rectifier. What else shall we do? What else can I talk about? So we know why that's in there and why it's that size. We know about the bridge rectifier. We know why that's in there. That's circuit protection in case we have an open circuit here. Even though it's a protection, if I'll show you later, I will disconnect one of the LEDs, and we'll disconnect that and make that open circuit, and I'll show you what happens. You'll probably find that that'll start burning first, and if we're lucky we may get that blowing up, but we won't have no fires. But once we've lost that and that, it just leaves us with this, which gives a nice little 3 milliamp circuit there, so it's not enough for it, dampens things down, it's not enough for it to catch any fires or anything like that. So what else can we talk about on this? So safety. yeah, you always remember, I probably mentioned it all earlier, messing about with these, you've got to know what you're doing, because these are not isolated. Basically it's not isolated from the mains, so you know, effectively you've got 336 volts DC, and the only thing that's bringing it down to a safe level are these components in here, these LEDs. So always go careful if you have one of these fitting dying on you, don't put your fingers in it if you can, because you never know. So that's simple. Any more calculations we can do? Yeah, we verified, I think we verified everything, why everything's in there. Now I think what I want to do is just to show you guys why this needs to be a closed circuit. Then basically it can't be open, because that's when everything starts burning up. I know that's rated at 20 volts, and that's the capacitor's rated at 36, which is rule of thumb design for your output voltage. Your output voltage at 10 volts should put a electrolytic in there that can manage 20 volts. However, if we was to open this circuit here, you'd have a lot more than 36 volts on that, you'd have a lot more than 20 volts on that. So I think what we'll do, I'll warm the soldering iron up and take one of the LEDs out, open the circuit. Actually I might actually just desolder, where are we, sorry. I might actually just desolder that and open the circuit right up, and I'll show you. Right, let's turn the soldering iron on. Yes, I am doing this in one take. I don't know how long I've been doing it for. Let's have a look. Probably been talking a load of rubbish, but hopefully you can understand what I'm getting at and what I've spoken about. Right, let's have a look. I'm going to step out of the way once I do this. Like I said before, what you're going to probably see, you're going to see the mod start smoking, and if that's designed well, we may not see the electrolytic explode, but hopefully it will, just so I can show you. There will be no fires. Once that's exploded, if it does in that circuit, you're going to have a nice little 3 milliamp circuit running through it. However, there's going to be an high voltage there, but it's not going to be causing us any fires. Let's have a look. Let's just desolder this quick. Don't even know why I'm desoldering it, because I'm not going to put it back together, because it's going in the bin once I've done it. You bitch. That's 340 bloody degrees, why ain't that coming off? Come on, you can do it. Right, so we're going to have a high voltage on that, but there's going to be no, we got that off, there's going to be no load on it. So I'm going to step back, get this into view and end the video on this. Let's have a look, let's get it into view. I'm going to switch it on and I'm going to stand back, enjoy. So I can't stress anymore, if you do buy one of these and it fails on you, throw it in the bin, don't even mess about trying to fix it. So try and get it into view so you can see it. Because I have seen videos on YouTube where folks have actually mended broken ones and took LEDs out and bridged them out, and I don't think that's a good idea. Anyway, let's switch the soldering iron off. Put some power through it and enjoy. I'm going to get out of the way. You can hear summer. Yeah, I can see smoke, that'll be the MOV. Let's see how that fails. The MOV's doing its work. Once that goes, if it don't fail short, we're going to find that the electrolytic's going to explode. So I'll leave it there a couple of minutes. Although we got smoke there, it's not going to cause a fire, because the MOVs are designed not to. I'll give it another minute. If we get no explosions, what I'll do, I'll take the MOV out of circuit and switch it back on, and then you'll understand why we got MOVs in circuits. At the moment it seems to be doing its job. Because it's only a 20 volt rated MOV, it's smoking. Because we got more than that, we effectively probably got around 300 volt DC running through it. So the MOV's doing its trick. It will smoulder away, and it will probably get to a point where it melts together and forms a little circuit there. I think what I'll do now is switch it off and take the MOV out, and then you'll see what happens without the MOV. So that's off at the moment. Yeah, the MOV is actually doing its business. It's turned black. The capacitor's still there, not even bulging one bit. Now watch happens when I take the MOV out and switch it back on. So the MOV is out, the MOV has done its trick. Now I've taken it out, and enjoy this. Let's get this in epoxy cheap bloody video stand. Right, I'm definitely stepping out of the way now. Anything happening? Hey, there you go. So that was a demonstration of a electrolytic capacitor blowing up because there's too much voltage running through it. So like I said before, every component in that circuit is there for a purpose. And the MOV did its trick. The MOV would have just failed short. But at the moment, that's really made a good job of that. Anyway, I'll leave you with that. Any questions, leave it in the comments. If you like it, give it a thumbs up. Thank you.